A little about me. So in addition to being the CEO of Psionic, I'm also affiliate faculty at UCSD and the University of Illinois at Urbana-Champaign in their bioengineering departments as well. And usually when I give these talks, I like to start off with a commercial that the University of Illinois made that they play at the halftime of football games.
Can we fit him?
How did they do that?
What did you do?
Where's the English building?
Could you go over that again?
Hey, can I check that?
When's that paper due?
Can I tell you my idea?
How can we make it cheaper?
Do you think this will work?
How did that feel?
So if you couldn't tell, that was me at the end of that video there. But I like that video in particular because it highlights the journey of starting off as a young kid who's curious about the world all the way to getting to these muscle-powered, neurally controlled bionic limbs. And for me personally, the journey started actually when I was 7 years old. So I was born in Chicago, but my parents are from Pakistan. And I was visiting Pakistan for one of the first times, and that was the first time that I had met someone missing their limb. And she was my age, missing her right leg, living in poverty, and using a tree branch as a crutch. And that's what actually inspired me to go into this field. And so I came back to the United States, and like most South Asians, I wanted to become a medical doctor. And my parents wanted me to become a medical doctor as well too. And so I went to Loyola University Chicago and was a biology major studying pre-med, and I took my first computer science class in my sophomore year, and I absolutely loved it. I loved everything about engineering and coding and building my own things. And I realized that if I became a straight up MD, I wouldn't get to do any of the cool things that I was learning in my computer science classes. And so I wanted to figure out a way to merge prosthetics with the engineering side of things. And right down the street, there's a hospital in downtown Chicago. It used to be called the Rehabilitation Institute of Chicago. It's now known as the Shirley Ryan Ability Lab. It's the #1 rehabilitation hospital in the US for like the last, I think, 38 years now. And they had made these huge breakthroughs in these neurally powered bionic limbs. And this was around 2007, 2008. And so this is Amanda Kitts, and she is wearing this arm that was designed by Dean Kamen's group and sponsored by DARPA. And she had this surgery that was done that rewired her nerves so that when she tries to imagine bending her elbow or rotating her wrist or making a pinch, her muscles are rewired so that they can respond, and they can pick up on that using muscle sensors, and she's able to do all these different tasks and activities of daily living. And so this was just this incredible combination of like electrical engineering, computer science, along with clinical medicine, physical medicine, rehab, neurology, and I was like, this is exactly what I want to do. Now the biggest problem was that the arm that you're seeing in there, right? I mean, it's meant to be a prototype, but it's a very expensive one, right? It can cost like hundreds of thousands of dollars just to make that, right? And it can be very fragile as well too, given all the components that are in there. And it turns out that there are over 10 million people with hand amputations across the entire world. 80% of them are in developing nations, and less than 3% have access to affordable prosthetic care. And the most prevalent prosthesis that's on the market is what you see on this man's right side. This is a hook prosthesis. So basically it's two steel pincers with a bicycle cable attached to your shoulders. When you squeeze your shoulders together, the hook will open, and when you relax your shoulders, the hook will close. And so you have to use your shoulders to control it, so it's not necessarily as intuitive as your nerves controlling it directly or your muscles. This is a technology that hasn't necessarily changed since the Civil War era of the United States, right? And it looks like a hook, right? On this man's left hand is what we call a myoelectric prosthesis. Myo meaning muscle, and electric meaning, well, electric. And so he's got two muscle sensors, EMG sensors, that he places over his wrist flexor, wrist extensor. He can get that hand to open and close. And the next step up from that is what we call a multi-articulated hand, where you can move like individual fingers. There's multiple motors inside the hand. But at that level, things get very fragile. They get very, very expensive. They're super slow. They get heavy. And on top of that, with all of these hands, if you try to touch anything, you actually can't feel it very well either. So you don't have that haptic feedback. And so we wanted to solve those challenges in particular. And so we employ advanced muscle control that allows you to do more than just open and close the hand. You can do various grips and then eventually individual finger control too using AI. we made the hand super strong using very low-cost materials, so it's very durable. And also, we were the first bionic hand on the market to give users touch feedback. And we'll be touching on all of those things, starting with the control. And so to control this hand, as I was mentioning, we use sensors called electromyographic sensors. And so for those of you who aren't familiar with EMG, you're probably familiar with EKG, right? So that's the thing that you see on like TV shows and ambulances when they have that sensor over the person's heart, and you see that monitor in the background that goes beep, 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 right? And then if they die, it flatlines, beep, right? So imagine that same sensor, but instead of placing it over the person's heart, you place it over their muscles, and then when you're not doing anything, you see this kind of flat line of activity, and then when you flex your muscles, you'll see this huge burst of activity because it's recruiting all the neurons in that area to make a giant muscle contraction happen, and that muscle contraction is amplifying all the electrical signals enough so that you can actually read it on your skin. So I ended up finishing my bachelor's in biology at Loyola. I got a master's in computer science there. I taught there for a couple of years before going down to the University of Illinois at Urbana-Champaign, where I got another master's in electrical and computer engineering, PhD in neuroscience, and then left medical school to do this because this was a lot more fun than finishing medical school. But when I joined the PhD program at the University of Illinois, there was no one really doing prosthetics there, and the closest thing we had was I worked in the lab of an aerospace engineering professor doing brain-machine interfaces, so Professor Tim Brettel. And we were working with a lot of algorithms and neural interfaces there. And so this next video shows when I have 8 channels of EMG sensors placed on my on my forearm, and you can see all the electrical activity happening when I'm doing different movements with my hand.
So here's the MATLAB showing all 8 channels, and if I squeeze, you can see all channels are active. If I flex, extend, do a pinch, 3-finger grasp, hand open, and hand close.
And so the important thing to note here was that as I was doing every single one of those different grasps, there's a different pattern of muscle activity that's happening. And because that's unique, we can actually train a machine learning algorithm or an AI algorithm to detect those different movements and then have a device respond to those different movements. But what I really wanted to do was to make bionic limbs. And so this was around 2013, 2014 when we saw a huge boom in consumer 3D printing, right? So this is the MakerBot Replicator 2X. This was the first 3D printer that we had ever received. And we had established a collaboration with the Shirley Ryan Ability Lab, but it was 2.5 hours north of Champaign in Chicago. And we got very limited access to the prosthetics that were there. And so we were like, we're at the University of Illinois. It's one of the best engineering schools. Why don't we develop our own prosthetic limbs? And over the last 10 years, we've actually gone through 9 different generations of the hand, starting with this one that you see all the way on the left, which was based on an open source humanoid robot called InMove by a French designer, and we modified it so it was just the arm and we could control it with our hands, and then successively each hand would get smaller and more packed with sensors as well at the same time. And in the spring of 2014, we met this guy. So this is Dave Krupa. He is the co-founder of a nonprofit organization known as the Range of Motion Project. And their mission is to provide prosthetics to those who can't afford them, primarily in Guatemala and Ecuador. And he's an alum from the University of Illinois. He was coming back to win some award for starting this organization, and he was talking about deploying prosthetics in resource-limited settings. And so I was like, I have to talk to this guy. This is exactly what I want to do. So I went to his talk, told him we were 3D printing our own hands, and asked him if he might be interested. And he was like, yeah, maybe. And the next day I showed him around the lab, and then I didn't hear back from him again. That was actually kind of sad. But 2 weeks later, I get this email from him that literally said, dude, I felt this vibe between us when we met, and we got to figure out a way to work together. And that's when Dave's and my bromance began. And so 2 weeks after that, he sends me another email saying that he was able to arrange from the US Embassy in Quito, Ecuador, to have me and another graduate student go down there and actually test our prototype of our hand on a patient. And we were like, this is the opportunity of a lifetime, right? The problem was that we had that hand all the way on that arm that was all the way on the left, and the motors and the electronics are actually located in the forearm. But if you still have your forearm, you can't physically place that stuff there. So we had to figure out how to move all that stuff into the hand itself. And so we worked with another open source design from an organization called Open Bionics, and we put all of our own electronics in, and that's Mark II of the Ability hand that you see on the bottom left with the blue tips on it. And we had to put that together that summer, and the day before we flew out to Ecuador, we didn't have anything working. But we figured we're gonna be in Ecuador for about 2 weeks, so we'll bring everything down there and we'll figure everything out when we get there. So fly down there, Dave picks us up from the airport, and the first thing he tells us is that we've got a meeting with the US Embassy tomorrow and they wanna see everything working. And we were like, oh great. So this is the beginning of basically 2 weeks of all-nighters in trying to get this hand to work. And we got it, so we immediately went to the hotel room and I hooked myself to all the sensors, and we got to a point where if I flexed my wrist really hard, I could just barely get this hand to close. And if I extended my wrist really hard, I could barely get this hand to open. And the way it's supposed to work is, I make a 3-finger grasp or like a key grip or like a pinch, and the hand is supposed to respond accordingly. But we had to do something, right? So this next video shows our first attempts at controlling this hand in the hotel room to try and grab this bottle that was on the table.
Yeah? Okay. Are you recording or not yet?
I am.
Okay, so maybe the Powerade bottle was a little bit too big, and so we decided to switch over to a smaller Coke bottle. All right, so maybe we need to reprogram some stuff as well too and try again. And this time, we were able to grab the bottle. And so, again, this wasn't how it was supposed to work, but we figured, again, we have to show the US Embassy something, so we took this with a giant breadboard with all the wires through US Embassy security and showed them this demo, ready for them to be like, this is what we spent our money on. And to our surprise though, we did this demo and they were completely floored. And that was because they'd never seen a robot in their lives before. They didn't know how this was supposed to work, so they saw me just controlling this with my arms and they were like, wow, next week we're thinking when you do this with a patient, we're gonna have 3 newspapers and 2 news crews come out and cover the event. And we were like, oh my goodness, okay. The bar is set super high now. And so they asked us questions like, oh, where are you guys from? So we said, we're from the University of Illinois. And they said, you're from the University of Illinois. In that case, we're gonna bump you up to all the international news stations, because it turns out that at the time, the president of Ecuador was an alum of the University of Illinois, and any chance they got to take to promote the university, they took it. So if the bar wasn't set high now it was set super high. And so the next day we met our first patient ever. So this is Juan Suquillo. He had lost his left hand 35 years prior due to a landmine explosion. He was in a border war between Ecuador and Peru. He was in the Ecuadorian army. And this picture shows his first attempts at trying to control our hand, and he wasn't able to do it. And to make matters worse, he was actually going to be flying out to Brazil the next day, and he wasn't going to be back until the day that the media was coming. So we basically had one chance to get this right in front of international news stations, right? No pressure. Fast forward to the following Thursday, the day that the media was coming. The night before, Dave Krupa tells us he's going to pick us up at 6 a.m. The media's coming at 9 a.m. and whatever we have working at that point, we're going to have to roll with. 6 a.m. rolls around. Mary, the other graduate student, and I, we've been up for about 32 hours straight. She's looking at this giant mess of a breadboard, trying to figure out what's wrong. I'm looking at hundreds of lines of Arduino code, trying to figure out what might be wrong there. And at 6:08, I noticed this one line of code that looks a little bit off. So I send Dave a text message. I'm just like, I think I might have found something. I just need a couple more minutes. And he says, okay. And it turns out that one line of code had 2 variables switched on the opposite side of an equal sign. And as soon as I switched those 2 variables, everything started working. When I made a pinch, the hand made a pinch. When I made a fist, the hand made a fist. And had Dave come to pick us up on time, we wouldn't have figured it out. So we were actually lucky that he was late. So for any of you who came late, it's okay. I forgive you. But it's one thing for it to work on me, it's another thing for it to actually work on a patient. So we figure that Juan's going to get there an hour before the media gets there. We'll hook him up to all the muscle sensors and then make sure everything works. Media gets there, it'll be smooth sailing. 9 a.m. rolls around, the media is all there, and Juan doesn't get there until 10 a.m. So again, we've got one shot to get this right in front of international news stations, and the media is already annoyed that they had been waiting this long. So we hook him up to all the muscle sensors, and the first thing we do is we check to see if we can read his signals, and every single channel is dead. And I'm like, oh my goodness, what else could go wrong at this point, right? So Mary and I, we go into debug mode. We're trying to figure out what's wrong with this giant rat's nest of a breadboard, while Juan and Dave are telling the backstory of the range of motion project and how Juan lost his hand, just to buy us enough time to figure out what's wrong. And so we checked the voltage across some of the areas, and we noticed it wasn't giving us the right value. And usually what that means is that there's something wrong with your power supply. We were powering this thing off of 2 9-volt batteries, and we had noticed that one of the 9-volt batteries had puffed up to about double in size and was burning hot to the touch. And had we not noticed it at that point, we might have been on the news for a different reason. But fortunately, I had a fresh 9-volt in my pocket. I took it out, and we hooked it up properly, and all the muscle signals appeared. So it was just like, okay, crisis averted. But it's one thing for us to read his muscle signals. It's another thing for the AI algorithms to respond and the biomechanics of the hand to respond accordingly as well. So the way this works is that Juan would undergo a 2-minute training procedure to train the AI algorithm to recognize his muscle signals. When the hand would turn on, it would do different movements. It would like hold a pinch, and you're supposed to mimic that with your residual limb. Hold a pinch for 15 seconds, hold a fist for 15 seconds, hand open for 15 seconds, key grip for 15 seconds, relax, and then you're supposed to be able to then control it. You ask Juan to control it, and then the hand should close, right? So we go through this 2-minute training procedure. The hand opens up, I ask him to close it, and nothing happens. And again, I'm just like, what else can go wrong at this point? And so this is completely serendipitous, but I happen to be Muslim, and Juan happens to be the leader of all the Muslims in Ecuador. And to put this in context, Ecuador is a 99.9999999% Catholic country, so for me to A, meet another Muslim there, but B, meet the leader of them, is the chances of that are next to impossible. So we found this out after we had met, and so he turns to me and he looks and says, Bismillah, say Bismillah. And for those of you who don't know, Bismillah is literally just invoking the name of God. That's what Muslims say before they start anything. And so I'm just like, Bismillah, okay, Bismillah, and I hit the reset button on the microcontroller. The training procedure starts all over again. He holds a pinch for 15 seconds, fist for 15 seconds, hand open for 15 seconds, key grip, relax. I asked him to close the hand this time, and the hand closes. And the media comes rushing around the table, asking him how it feels for this to work. And I take a step back, a huge sigh of relief, and I'm thinking in my head, you're a man of God. And so this next video shows one of those international news stations covering the events of that day.
Un quiteño es el primer beneficiado de una prótesis de mano con ayuda en su financiamiento. El programa es realizado por jóvenes de la Universidad de Illinois en Estados Unidos.
Juan Suquillo es excomandante de guerra. Fue así como perdió parte de su brazo. De esto han pasado más de 30 años.
Varios miembros de mi pelotón sufrieron heridas y particularmente la mía me cobró el brazo izquierdo.
Gracias al avance de la tecnología, hoy puede acceder a una prótesis.
Parte de mí ha vuelto.
Jóvenes ingeniosos y con un gran empeño por ayudar al prójimo más necesitado han desarrollado una prótesis de brazo mioeléctrico con la posibilidad de retroalimentación sensorial, es decir, sentir como una mano de verdad.
So a couple of things I want to point out here, right? The hand that you see on the screen, it's 3 times the size of an average adult human hand. It has wires going everywhere, plugged into breadboards, power supplies, my laptop, and the wall. And despite that, Juan said that he felt as though a part of him had come back. And that was because he made a pinch with his left hand for the first time in 35 years. In fact, he had forgotten how to make a pinch, and we had to retrain his brain by placing a mirror in front of his amputated side, reflecting his right hand, tricking his brain into thinking that his left hand was there, so that when he made a pinch with both sides, it reactivated his muscles, and then that was enough to drive the prosthesis to move. So when he said that, that's when I realized that if I stay in academia, if I finish med school and go work in an academic hospital, this just ends up as a journal paper. if we want everyone to feel the exact same way that Juan did, we had to commercialize the technology. And that's when Psyonic was born. So we came back to the university, we entered our school's business plan competition in 2015, we won that, the Illinois Innovation Prize in 2016, several grants from the National Science Foundation, raised a pre-seed round, seed round, and as of September of 2021, the latest version of the Ability Hand has been available nationwide. We have over 200 patients using it, 50 robotics companies as well, including NASA, Meta, Google, Apptronik. Mercedes is building cars with it via Apptronik as well too. And so that's what the hand looked like then, and this is what it looks like now. So this is retired U.S. Army Sergeant Garrett Anderson doing push-ups for one of the first times since his Army days. He can even do things like kettlebell swings. The hand can hold up to a max out at 140 pounds. It can do 100 pounds regularly. And you don't have to do all this extreme stuff too. You can do something as mundane as closing your laptop lid. Or for one of our first users, Tina, feeding her granddaughter for the very first time because she could hold the bottle with her bionic hand and the baby with her natural arm. And that's why we do what we do, right? To improve the quality of life for individuals who are missing limbs in particular. And so these are all the specs of the hand, but rather than read a screen, it's a lot better to have some show and tell on this too. So I'm going to invite one of our employees and users of the Ability Hand, Dale DeMasi, to the stage. Can we give him a round of applause, please? Thank you, Dale. So Dale is one of our creative specialists at Psyonic over in San Diego, where our headquarters is. And we made a special version of the hand for him that's a clear version. So this is our latest version of the hand, but you can actually see all the internals. But he is actually controlling this right now just by using his muscles. And you can actually see that visibly because every time he fires his muscles, it lights up. Right, so you can see the orange lights will go down, and depending on how strong he's contracting his muscles, it determines the speed of those lights. But also, this is the first hand to give users touch feedback. So when he touches the fingers, there are blue lights that actually go in the opposite direction, so he can actually feel when the hand is actually touching an object. And the harder he touches, the faster those lights travel, and he can feel it through a vibration that is in his residual limb. Thank you, Dale. So our hand works with multiple control systems. That's one of the simplest ones where you have two muscle sensors. We can have like 8 muscle sensors. We can have, we've done it with like brain implants and neural implants, and we'll get into that in a little bit as well too. But when you're using those two channels, you can switch between different grips by just firing another open signal. So here's the power grip, right? I can open it again, switch to like a pinch. If you flex your muscles lightly, you can control the speed of it and go slowly. If you're at a rock concert, you can rock on. And one of our user favorites is the finger wave, where you can actually see all the fingers moving at once, right? So other things about this, the fingers are flexible, so they can take a beating, so I can smash it and it survives. I've climbed the roof of my house, dropped it 30 feet in the air, it survived. I've stepped on it. We put it in a dryer for 10 minutes. I arm wrestled the para-triathlete national champion and lost. And we've even done flaming board breaking with it, where we had 3 wooden boards, set them on fire, and we were able to punch through them as well too. So it's water resistant, so you can take it to the sink and wash it like you would a natural hand. It's super light and super strong as well. So this is actual carbon fiber that's on here. It weighs lighter than my own hand. This is about 480 to 490 grams. Average adult human hand is about 520 grams. This is an industry standard quick disconnect connector that I can put back on here. It'll recalibrate and turn back on. It's USB-C rechargeable, so the same way you plug in your phone, you can plug in your hand. Charge lasts about 7 to 8 hours a day. If you're out in the woods, you can use one of those portable power packs to recharge it as well too in an hour. But you can also charge your phone from your arm, which is a superhuman ability we like to give our users. I wish I could do that with my own arm, right? But the best part about it is that this is the hand is actually covered by Medicare in the US, and so we have a standard CPT code. And what that means is that we expanded access from about 10% of patients who could afford it to 75% of patients who could afford. And that's what we're all about, building the most advanced bionic limbs that are accessible for both humans and on the robotic side as well. And so just to show some other things about this, the fingers close in 200 milliseconds. It's the fastest bionic hand on the market. And so one of our first users was the para-triathlete national champion of 2018-2019, Dan St. Pierre. 3 minutes after he was fitted with the hand, someone threw him a water bottle and he was actually able to catch it.
All right, ready? That's it, right here.
And then very stupidly, I decided to challenge him to that arm wrestling match. And so they gave us the stadium at the University of Illinois, and unfortunately, I ended up losing. I should probably take this out of rotation just to save me the embarrassment of having to watch it over and over again. But someday I'll get my revenge on him. But if you guys remember that viral trend from many years back where if you have a partially filled bottle of water and you try to like flip it and make it land right side up, you can imagine that's a lot harder to do with a bionic hand, but we had one of our users, 17-year-old Kate Kettlehone, come to our offices, and she was just nailing shots all over the place. And you can see all these videos on our YouTube channel as well too, and we actually go into the science and engineering behind like what advantages and disadvantages people have in doing these things. But Kate, she nailed this shot in the stairwell where she landed it on the windowsill 2 stories up, and we were all pretty excited about it. And so if you guys remember Sergeant Anderson, so we can hook the hand up to a wrist rotator and he can do 360 degrees of wrist rotation, right? So we've made him superhuman. And then here he is punching through 3 wooden boards set on fire. And we wanted to do that on Shark Tank, but they wouldn't let us set things on fire. So we had to settle for Sergeant Anderson doing only 1 board live in front of the sharks. But if you guys recall, you're not going to see people doing things like that every day, right? Like punching through like wooden, flaming boards and things like that. But the idea is that if it can survive those tasks, then it should be able to survive your activities of daily living that are much less extreme than that, right? So in this video, you're seeing our user experience specialist, Annika Berlin, do things that she might do on a typical day where it's cooking, going to the gym, folding laundry, going out golfing, and then of course, since we're in San Diego, she actually goes out paragliding as well over the 1,200 foot. She can even go out with her friends and like take out a point-and-shoot camera, take pictures, hang out. The fingers are conductive, so they work on touch screens. And she can even go golfing. And while we were paragliding, they even let her do like 360-degree turns and everything too. So it was really cool that she was able to leverage her ability hand to do all of that stuff as well. And so if you guys remember that this is the first hand with touch feedback on here, we have 6 touch sensors that we place in here. So 1 on the fingertip, 1 on the finger pad, 2 on the outside, 2 on the inside. And I believe we have a dynamic range from like 10 grams to like over a kilogram with a 1 gram resolution that's on there. And we're always working on ways to improve our touch sensing and sensors through each subsequent iteration of the hand. But what this enables you to do is very fine manipulation of delicate objects. So this is 80-year-old triple amputee EQ Sylvester grabbing a hollow eggshell while blindfolded on his first try because of the touch feedback that's in the hand that he can both feel, and the hand can automatically respond by slowing down the grips through a contact reflex so he can grasp that without cracking it. And then if you guys remember Juan, our very first patient, well, 1.5 years ago, we flew back down to Ecuador, and finally, after 9 years, we're able to deliver him a hand that he now uses on a daily basis. And this is one of our favorite moments at the market. We grabbed our Nada Neo fruit and was able to And just a month ago, I went back down there and we actually fit our second patient. So everything that started with him is now being paid forward to the next set of users over in Ecuador as well. And so while we were doing all of this, we realized that if you're building a robot to do human tasks, well, we've optimized our hand for humans to do human tasks. So it makes sense that a lot of robots will end up using the same thing. And so I was mentioning that a lot of robotics companies are now using the hand too, including NASA and Apptronik. And so at NASA, they have the humanoid astronaut robot Valkyrie that they were developing, and they put our hands on it, and they're actually able to use it to do tasks that you might find on the International Space Station. And so this image is one of my favorites. So this is our user experience specialist, Annika, who you just saw, fist bumping the NASA humanoid astronaut robot with the same hand. And we can even pop it off the NASA arm and put it on hers, and she'd be able to use her muscles to control it. But there's this panel of buttons and knobs and switches that you might find on the International Space Station, and they were struggling to do a zipper that was on the wall. And it was primarily because they were using a pinch grip to do it, but the vast majority of the tasks that we do with our hands, 80% of them, are either a power grip or a key grip. And so Ani, she goes up to the zipper and she easily does it with a lateral grip or a key grip. And the NASA engineer is like, oh, we didn't even think about using the hand in that way. And this was really insightful to us because, again, our human users have done practically all the tasks that the robots are trying to do. So in a lot of ways, we have users who serve as training data essentially for a lot of the robotics use cases as well. And we have tutorial videos where we show like cracking an egg and like cooking and cleaning and the folding laundry. That's very useful on the robotics side to just kind of emulate how our human users are doing it as well. But we don't have to put the hands just on a humanoid robot. We can put them on robot dogs as well. And so this was with Professor Ji-Hyun Kim at the University of Illinois, where he has a Boston Dynamics robot dog. He has these two modular arms that he built. And then we put our hands on those modular arms. We then gave the hands lightsabers. And then I had a lightsaber duel against the Boston Dynamics dog. For the Star Wars fans in the audience, we refer to this as General Grievous's dog. I keep losing these challenges. I gotta start getting better at this. And so we don't need to put the hands even on a robot dog. We can just have the hands function autonomously on their own. And so for Halloween, we actually made the hand walk on its own, Addams Family style. Don't worry, I survived, but just barely. So putting that all together, right, where does that bring us to right now, right? Where we see these same hands being used on humans and being used on robots. And we're seeing a lot of the same tasks being done on both sides. And so this next video kind of highlights how we've designed it to work for both.
You know we don't play, stay out the way. Check out this look on my face. I'll come save the day, give me my cape. Look at I'm flying away. Five-star cream of the crop, go and make spot. Go and put the cherry on top. This one can't be stopped, giving them shock. It's really like that, don't believe me, just watch. Watch, 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 watch. Don't believe me, just watch. Watch, 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 watch. Don't believe me, just pulling up me and my friends. Big boy spins, just might start up a trend. You don't wanna go up against no
watch.
And so, that's where we're at right now, but where are we going with the future of this technology in particular, right? And so, as I was mentioning, we moved to San Diego about 2.5 years ago from Illinois. And one of the big reasons for moving there is that we're working with the Navy Hospital and UCSD on the next generation of these bionic limbs that are directly connected to your bones and your muscles and your nerves. And so we're working with the orthopedic surgeon at the Navy Hospital, Dr. James Flint, as well as Dr. Kate Hinchcliffe, who's a hand surgeon at UCSD. But the idea there is that instead of having these grips that you can control, that you could actually control each individual finger. And so we've actually collaborated with the University of Chicago as well on doing brain implants to actually control the hand. And this was actually featured on 60 Minutes last year, where there was a patient, Scott Embry, who was paralyzed in a car accident, and just by thinking, he was able to control our hand on a robot arm to shake the host of 60 Minutes' hand.
How you doing, Scott? Nice to meet you.
Nice to meet you, Scott. With volunteers including Scott Embry. And you can feel that.
I feel it on my fingertips.
Whose movement and sense of touch are limited by a spinal injury from a car accident. Computer ports in Embry's skull are wired to the motor and sensory parts of his brain. Electrodes pick up the brain's electrical signals that were intended for the muscles. A computer translates those signals to the robot arm.
Middle.
And they blindfolded him, and they stimulated the area of the brain corresponding to each one of the fingers, and he could tell which finger was actually being touched. And to kind of illustrate what this control is going to do for our users, we're going to do something fun here. So there's an app for the hand, there's an app for everything these days, right? And so I'm going to connect to this hand via the app. And if I could get a volunteer from the audience to come up and actually get a chance to control this hand. I see your hand shot up. All right, let's give him a round of applause as he comes up to it. And so what's your name? Eddie? Nice to meet you, Eddie. I'm Adil. And so this is what we're going to do. So what I want you to do is put your hand in front of the camera. Yep, just like that. And then start bending your fingers. Like you can count like with your fingers. Yeah. Yep. And so it's actually mimicking every single thing that he's doing, right? So his pinky moves, it's just doing real-time position control over Bluetooth over each one of the motors that's actually in the hand. And you can just like go crazy with your fingers, like wiggle them around, yep, and it'll respond accordingly as well too. So thank you, Eddie. Thank you so much. So the idea there is that in addition to things like robotic teleoperation, but we can use that as a training tool for the nerve implants to actually determine how to learn the mapping of what your fingers should be doing in a neural prosthesis. And so we're hoping that in the next 1.5 years or so that we'll start clinical trials on these nerve implants to actually get users to potentially play piano or type on a keyboard again. And that's what we see for the future, this seamless integration between humans and robots. But if we don't make it accessible, then we're not doing what we set out to do. We're not doing our job. So as I mentioned, by getting it covered under Medicare, we expanded access to 75% of Americans who can afford it, but that still leaves 25%, as well as the 80% of people in developing nations. And so for them, what we did is we started this initiative called the Ability Fund. And through the Ability Fund, a bionic arm and a leg and all the clinical services can cost between $100,000 to $150,000. And we're able to cover all of the clinical services and an ability hand for $25K, as well as donate a leg to Guatemala or Ecuador for $25,000 donations that are tax exempt. Thank you. And so we just fit our very first recipient of the Ability Fund, Ivan Krastev, who's a 16-year-old kid who was born without his left hand in South San Diego. And this was literally 2 weeks ago that he finally received a hand for the first time in his life, and this is his story.
My name is Ivan Krastev. I am 16 years old, and I am from South San Diego. When I was younger, I didn't really catch on to, I have a hand, that's whatever. But once I realized I became conscious of caring about others', opinions and how they looked at me, I really started to become self-conscious, like extremely self-conscious. I wouldn't go out if I had just a shirt on like this. I got bullied about it, but it's really whatever. My teacher, Mr. Bentz, showed me this link, and it was a robotic hand. He encouraged me to send an email. I didn't actually think the CEO would contact me back. The date came, that's when I came here and came for the first time with everyone else.
Can you do the other one? Can you actually make it close? You open, oh man, you're like a natural at this already.
Just before coming here, I didn't really want to have anyone feel pity for me having one hand, and you know, it's really cool to be able to come here and know that this exists literally not even a few miles away, and it's a really cool thing, honestly. It's just looking back at how I was thinking about like robotic limbs, just never had the real thought of being like in a physical place where robotic limbs exist with me in it.
What's up, buddy?
Yeah, Alex, it is. Oh my gosh, I thought it was black. It's green. Nice. That's insane.
That's the big surprise.
It is the big surprise. Oh my gosh, I can't believe it. Yeah. This is beyond what. This exceeds expectations, honestly. This is big.
And so if you're interested in learning more about the Ability Fund, you can go to ability.fund or scan that QR code. And with that, I'd be happy to wrap it up and take some questions.
Yeah, we awesome. Give it a round of applause. Just first off, what an incredible mission. You know, I don't think I can think of a more perfect use of robotics. So thank you for all the work you've done. You're also an incredible storyteller, so kudos all the way around. I think we'll wrap it up there. I don't know if Ideal has some time to stick around. Maybe people can come up and get a little bit of a closer look at the Ability hand. But one final time, a round of applause for Adil Akhtar of Psyonix.